Imagine a time before we knew. A time when the universe was just a quiet, static stage. It was 1912. In the cold, thin air of Flagstaff, Arizona, an astronomer named Vesto Slipher worked tirelessly. He was at the Lowell Observatory, a place built to chase mysteries on Mars. But Slipher pointed his 24-inch telescope towards something else entirely. He aimed it at the faint, fuzzy patches of light that were then called spiral nebulae. No one knew what they were. Were they clouds of gas inside our own Milky Way? Or were they something far, far more distant? He was about to find the first clue in a story grander than anyone could have imagined. Slipher wasn't looking for motion. He was studying their light, breaking it down into a spectrum of colors. Think of it like a cosmic barcode, but he found something strange, something that defied all expectations of a calm, unchanging cosmos. The light from most of these spiral nebulae was stretched out, shifted toward the red end of the spectrum. This phenomenon, known as redshift, meant only one thing. These objects were moving away from us, and they were moving at incredible speeds. It was a whisper from the void, a hint that the universe was not the serene backdrop we had always assumed it to be. The stage itself was alive, and it was expanding. The implications were staggering, but the data was just a trickle at first. Slipher meticulously recorded his findings, galaxy by galaxy. He saw Andromeda moving toward us, but almost everything else was running away. It was as if we were at the center of a great cosmic exodus. For years these observations remained a puzzle, a collection of curious facts without a grand theory to connect them. The scientific community took note, but the full picture was still shrouded in darkness. The universe was keeping its greatest secret, waiting for the right mind and the right tools to finally pull back the curtain and reveal its explosive origin. He worked in the quiet solitude of the observatory, under skies so dark you could feel the weight of the stars. The telescope was a brass and iron giant, a mechanical marvel of its time, moved by gears and weights. Each photographic plate had to be exposed for hours, sometimes across multiple nights, just to capture the faint photons that had traveled for millions of years. Slipher was a pioneer, charting unknown territory with nothing but light and glass. He was mapping the first movements in a cosmic dance, and he didn't even know the name of the song yet. He had heard the first faint echo of creation. The mystery deepened. The scene shifts to Southern California, to the magnificent Mount Wilson Observatory perched high above the growing city of Los Angeles. Here, a new, more powerful eye was turned toward the heavens, the 100-inch Hooker telescope. It was the largest in the world. Its gigantic mirror could gather more light and see deeper into space than any instrument ever built. In the 1920s, an astronomer named Edwin Hubble used this machine to settle the debate about the spiral nebulae. He proved they weren't gas clouds in our galaxy, they were entire galaxies themselves, island universes separated from us by unimaginable voids of space. Hubble, a charismatic and meticulous observer, then turned his attention to the puzzle Slipher had uncovered. He began systematically measuring the distances to these newfound galaxies. At the same time, he measured their redshift, their speed of retreat. He plotted the data, point by painstaking point. And then, in 1929, the pattern emerged. It was simple, elegant, and universe-shattering. The farther away a galaxy was, the faster it was moving away from us. This wasn't a random scattering. This was a clear mathematical relationship. The universe wasn't just expanding, it was expanding in an orderly, predictable way. This discovery, now known as Hubble's law, was the second crucial piece of the puzzle. It transformed our understanding of the cosmos. If everything is flying apart, you can run the movie in reverse. What do you find? A moment in time when everything, all matter, all energy, all of space itself, was crushed together into a single, infinitesimally small, incredibly hot and dense point. This was the seed of the Big Bang Theory. The idea of a static, eternal universe was shattered forever. Our universe had a beginning. It had a birthday. And we were living in the aftermath of the most spectacular explosion of all time. The Hooker telescope was a temple of science. Its massive dome, 100 feet across, would rumble open to the night sky. Hubble would ride a small platform up to the telescope's prime focus, sitting inside the giant metal lattice in the cold mountain air. He would guide the telescope by hand, keeping a star perfectly centered for hours on end. This was the painstaking work that revealed the grandest truth about our universe. The evidence was clear. Galaxies were not just moving through space. Space itself was stretching, carrying the galaxies along with it for the ride. For decades, the Big Bang was a powerful theory, but it had a problem. If the universe began in a hot, dense state, there should be some leftover heat, an afterglow from that initial fireball. Scientists predicted that as the universe expanded and cooled, this primordial light would have stretched into microwaves. It should be everywhere, a faint uniform hum filling all of space, but for years, no one could find it. The theory was compelling, but it lacked this one critical piece of evidence. The smoking gun of creation remained hidden, waiting to be discovered not by a grand design, but by a complete accident. The year is 1965. At Bell Labs in New Jersey, two radio astronomers, Arno Penzias and Robert Wilson, were working with a strange-looking antenna. It was a massive horn-shaped receiver, originally built for satellite communication. Their goal was to map faint radio signals from the Milky Way, but they were plagued by a persistent, annoying hiss. It came from every direction, day and night, no matter where they pointed the antenna. They checked their equipment, cleaned the antenna, and even removed some pigeons that were nesting inside. But the noise wouldn't go away. It was a uniform, low-energy microwave signal. Penzias and Wilson had no idea what they had found. They thought it was a problem with their instrument. But just down the road at Princeton University, a team of physicists, led by Robert Dick, was building a detector specifically to search for this cosmic afterglow. When the two teams finally connected, the truth became instantly clear. The annoying hiss that Penzias and Wilson had discovered was not noise. It was the echo of the Big Bang. It was the oldest light in the universe, the cosmic microwave background radiation. It was the faint, cooled-down remnant of the moment of creation, finally detected after traveling through space for over 13 billion years. This discovery was a monumental triumph for the Big Bang theory. It was the proof everyone had been waiting for. The universe was not just expanding from a single point. It had begun in an unimaginably hot state, and the leftover heat was still here, bathing our planet and everything we can see. Later missions, like the COBE and WMAP satellites, would map this background radiation in stunning detail. They revealed tiny temperature fluctuations, the seeds of all future structure. These were the faint ripples in the early universe that would eventually grow into the vast clusters of galaxies we see today. The story doesn't end there. It only gets deeper and more mysterious. As our tools improved, we began to see the universe in ever finer detail. The Hubble Space Telescope, launched in 1990, gave us a crystal-clear view, free from the blurring effects of Earth's atmosphere. It showed us the grand structure of the cosmos. Galaxies aren't scattered randomly. They are arranged in a vast, intricate network of filaments and voids, a cosmic web. This structure is the direct result of those tiny fluctuations seen in the cosmic microwave background, grown over billions of years by the relentless pull of gravity. And now, we have a new eye on the universe, the James Webb Space Telescope. Launched on Christmas Day in 2021, this infrared observatory is a time machine. Because light takes time to travel, looking deep into space is also looking back in time. Webb is so powerful it can see the first galaxies beginning to form, just a few 100 million years after the Big Bang. Its first images, released to a waiting world, were breathtaking. They revealed galactic nurseries, dying stars, and galaxies crashing together, all with a clarity and depth we'd never seen before. Webb is pushing our cosmic horizon back to the dawn of time. With Webb, we are now directly witnessing the era when the first stars ignited, ending the cosmic dark ages. We are testing the Big Bang model with unprecedented precision. We are piecing together the story of how those first, simple galaxies evolved into the complex spirals and ellipticals we see today. But as always, new discoveries bring new questions. Observations showed that the expansion of the universe is not slowing down as expected. It is accelerating. This led to the idea of dark energy, a mysterious force that seems to be pushing space apart, making up nearly 70% of the universe. So where are we now, on this day in 2026? Scientists are using Webb to hunt for the very first stars, known as Population 3 stars, forged from pure hydrogen and helium. They are trying to understand the nature of dark energy and dark matter, the invisible scaffolding that holds galaxies together. The Big Bang Theory is stronger than ever, but it is incomplete. It tells us how the universe evolved, but not why it began. The grand mystery remains. We are still wanderers in the cosmic dark, following the echoes of a distant explosion, forever reaching for the light.